This video will introduce you to the process of how to add two or more vectors. We'll start out with some basics about adding vectors, and then we'll get down into the nitty-gritty of exactly how to do it. The first thing we're going to learn about is the fact that when you add two vectors together, you get something called a resultant vector. It's kind of like when you add two numbers, you get a sum, or when you subtract two numbers, you get a difference. So we call the thing that we get when we add two vectors together the resultant vector. A couple of important points about adding vectors. You'll see that I have three vectors here, a 5 meter vector, the green one, a 3 meter vector, the pink one, and an 8 meter per second vector, the blue one. Could I add the pink and the blue vectors? If you answered no, you'd be correct. Vectors must have the same units to be added. Now, what would happen if I would add the green and the pink vectors? They have the same units. One is 5 meters in magnitude, the other is 3 meters in magnitude. So clearly, if I add them, I'd get 8 meters, correct? Well, if I think about what those really are as those being displacements, if I went 5 meters east and then 3 meters west, I wouldn't end up with a total displacement of 8 meters. So it's important when we're adding vectors that we're not only paying attention to magnitudes, but also paying attention to the direction of those. Here are some steps for adding vectors. The first step we're going to do is draw a diagram of your problem, making sure that the vectors that you're adding are arranged tip to tail. Then we'll split each vector into components. And of course, we need to pay attention to whether those components are positive or negative. After that, we're going to add the x components together to get the x component of our resultant vector. And then we'll do the same thing for the y components. Next, we'll draw the resultant x and y components. And of course, we're going to make sure that those resultant x and y components are tip to tail. We'll find the magnitude of the resultant using the Pythagorean theorem. And finally, we'll find the angle of the resultant so that we can give its direction using trigonometry. Let's practice with an example problem. This example problem, Emily's on the hockey rink, and she makes two consecutive movements, 14.5 meters south and 24 meters at an angle of 15 degrees east of south. We're asked to find Emily's overall displacement, which really is just a fancy way of saying add these two displacement vectors together, so that we'll find a resultant vector. We'll start with step one, which is to draw a diagram of our situation. We'll start out at 14.5 meters south. That vector would look something like this. And of course, I like to label the magnitude of each vector as well. 14.5 meters. And my second vector says that it's east of south. So it's often useful when I am given a direction like that to draw a small xy axis before I draw the vector itself. East of south would look something like this, where that angle of 15 degrees would be right here. And that's a magnitude of 24 meters. So I've drawn these two vectors separate from each other to start off, but as it says in our steps for adding vectors, to add them together, they have to be tip to tail. So there would be one way of drawing them tip to tail. And I could put what I put in here for the direction. I can add that in right here as well. Then I'm going to draw my resultant vector. If I draw my resultant, it starts out at the tail that's unpaired and goes to the tip that's all by itself. To be able to add these two vectors together, I then have to split each vector into its components. So even though I have them drawn in this thing together, I'm going to draw these two vectors separately as well. Let's call this vector x1, and this vector x2. So the x component, that might be confusing, talking about an x component of a vector named x. So maybe we don't call it x. Let's call it d, since it's a displacement. So this will be d1, and this will be d2. So d1x and d2x are something that we'll need to find. We've talked about finding components before. Hopefully it's something you're comfortable with. And then we have d2x and d2y. And I just realized I should have written d1y over here. So looking at d1, I noticed that it's pointed downward. It's pointed south. Vectors that point directly up or directly down do not have an x component. So its x component is 0. Its y component is that 14.5 meters. But since it's pointed downward, that y component is negative. It's an important thing to pay attention to. For my second vector, I'm going to have to find those components using trig. So, kind of just listing some of the things that I know with this vector. I know this angle here is 15 degrees. Draw the components of this vector. My x component would go downward like that. Sorry, my y component goes downward like that. My x component goes straight across. Looking at this triangle that I've made, I could use the sine function to find my x component, because the sine of 15 degrees is opposite over hypotenuse. My hypotenuse, remember, is equal to 24 meters. So if I multiply that 24 meters by the sine of 15 degrees, I can find the x component of my vector. That x component ends up being 6.21 meters. I could use the cosine function to find the y component, because the y component is adjacent to my angle. So the sine of 15 degrees would be the y component divided by the hypotenuse. Or in other words, the y component is 24 meters times the cosine of 15 degrees, which is 23.2 meters. Notice how that y component is pointed downward? That's important to note, because that means that it's a negative y component. Since the x component is pointed to the right, it's positive. So now that we've found the components of each of our vectors, we can move on to the third step, which says to add the x components together and to add the y components together. So when I add those two x components together, I get the x component of the overall displacement is 6.21 meters. And when I add the y components together, I find that the y component of the overall displacement, or the resultant displacement, is negative 37.7 meters. Moving on to the fourth step of my process, I'm going to draw these two components. So 6.21, and it's a positive component, so it would be pointed to the right. And then negative 37.7. Negative, so it's going to be pointed downward, and it's a pretty long vector there. I put those two vectors, those two components, tip to tail. So I see my result is that green vector. Notice how that green vector looks pretty similar to the green vector I drew up above. As long as you do your drawings with relatively similar magnitudes or relatively accurate magnitudes of your components, it should help you out in knowing if you've done things correctly. I'm adding in the magnitudes of my components onto my vector here. And in step 5, I use the Pythagorean theorem to find the magnitude of my resultant. So this would be vector D here. And vector D has a magnitude that is equal to 38.2 meters. Because D is a vector, I also need to find a direction. When I'm finding that direction, I find it useful to draw an XY axis, and my XY axis is always at the tail end of my resultant vector. Here's one angle I could solve for to give a direction. I typically use the tangent function because that uses the components, which are more likely to be accurate than the hypotenuse of my triangle. So the tangent of my angle theta would be opposite over adjacent, so 37.7 meters divided by 6.21 meters. To get the angle itself, I have to use the inverse tangent. So the inverse tangent of 37.7 meters divided by 6.21 meters gives me an angle of 80.6 degrees. And then I have to interpret where that 80.6 degrees is. One way of saying 80.6 degrees would be that it's negative 80.6 degrees, ISP, in standard position. I could also say 80.6 degrees south of east, or 80.6 degrees below the positive x-axis. You could also potentially solve for the other angle, depending on how you drew your diagram. So it's possible that instead of 80.6 degrees, you had found 9.4 degrees. If that were the case, it would be east of south or to the right of the negative y-axis. Adding vectors like this is commonly used in physics for dealing with displacements, velocities, and accelerations that are in multiple dimensions. And we'll also use it later in the year as we deal with forces. We'll get more practice in class when we meet next.